Good morning, friends. We'll start with our third lecture of physics, that is magnetic field due to electric current. Part 3. This is so children, this is our third lecture. This is our third lecture. So last lecture, what we saw, we'll just have the review. We'll have the revision of the last lecture. So last lecture we saw magnetic dipole moment. Then we saw magnetic dipole potential energy. Then we saw Bart-Savarit's law. Then the applications of Bart-Savarit's law we have seen last lecture. That is the Bart-Savarit's law for the straight conductor. And secondly, we saw it for the circular loop at the center where we find out the magnetic field. And then we saw force due to the two parallel conducting current wires. Once the two wires are parallel, the current is in the same direction, we have force of attraction, and when the current is in the opposite direction, we have repulsion, force of repulsion. So today, next part which we are going to see is regarding the third application of Bart-Savarit's law, that is along the axis, that is the magnetic field along the axis of a circular loop. Then after that, we'll go for the Ampere's law and its application for there are three applications of Ampere's law. One is for the straight conductor, and then we apply Ampere's law for the solenoid, in which the wire is wound in such a way, it is wound to a hollow cylinder, and then it is connected to electric field is applied to it. Or third one is toroid, when the solenoid is taken in the form of a circle, or you can say it is like a tire in the car, the tire of a car. So these three things that we are going to find out the magnetic field by applying the Ampere's law. Now we'll go for the presentation. So we'll have magnetic field at the axis of loop of current carrying loop. Then we'll see Ampere's law, and its application. There are three applications. We are going to see them. So we'll go for the presentation. Yes. Now we'll see the axial magnetic field produced by current in a circular loop. So see here, this is the loop. This is a loop. See the figure, please. Concentrate on the figure. So this is a loop, circular loop. You can see it is of radius r, and you're taking the element dl here, dl, small element dl, or you can say it here. And you want to find out the magnetic field along the axis. So you can see that this is the z. This is the z axis also, and on this axis you're finding out the electric field here. Electric field at point P here. Now this is in xy plane. You can see this loop, it is in xy plane. Okay, so see here a circular loop of a wire carrying a current I, and radius of the loop is r. So see, this is the radius of the loop. The magnetic field, now we are going to see the Bad-Savarit's law we are going to apply. The magnetic field at a point P at a distance r from the element dl on the loop using Bad-Savarit's law. So see here, dB equal to, so this is dB. dB is equal to, so we are taking a small element dl, so we'll consider dB. dB is equal to mu 0 upon 4 pi in a Bad-Savarit's law. That is I dl vector cross r vector mod of it divided by r cube. Now dB is equal to mu 0 I dl upon r square. So where r square equal to, if you consider the right hand, this one Pythagoras theorem, so r square is equal to capital R square plus z square. So see here, you can see this r square. So this is at the distance here. This is P is at the distance of r from this element. So this is as good as hypotenuse. You can see. So r square is equal to z square plus r square. So dB is equal to mu 0 upon 4 pi IDL, and for r square you're going to substitute r square plus z square. So you may note down, children. Then remember that the net contribution along the z axis is obtained by integrating dBz, which is equal to dB cos theta over entire loop. Why? Because if we take this dB perpendicular, okay, this will cancel. This will cancel, and because of this it will be addition of all this will be 0, and whatever adds up is because of the dB cos theta, which is along the z axis. So you're going to add all this to take the summation, or rather integration. So we take it as dB cos theta. The sine theta will get cancelled if you take this angle theta here. So its component is sine theta and cos theta, but here sine theta will get cancelled, and because of that we have cos theta. So cos theta is equal to, we know by trigonometry, r, capital R upon r, capital R upon small r, which is equal to capital R upon, now you know what is r, it is under root of z square plus r square. Now bz equal to, now integration, now bz db, and it is integration of all the dbz along this axis. So that is bz equal to integration of dbz, that is equal to mu 0 upon 4 pi I integration of dl upon z square plus r square dot cos theta. Now that is equal to mu 0 upon 4 pi I, and integration again r dl upon z square plus r square. Okay, now for cos theta you're going to write what? r upon z square plus r square. So this your term, you're going to write it. So as it is, this is raised to 1 and this is raised to half. So that will become 3 by 2. So whatever is the constant term, take it out. Radius is not going to change, take it out. So the constant terms are taken out of integration. Then mu 0 upon 4 pi I r and integration. Now this integration we have taken for the numerator. No, total one, dl upon numerator we're taking, and then z square plus r square uh, under cube 3 by 2. Okay, then we can see that mu 0 upon 4 pi, this term is as it is. Only now dl. Now see, if you see, this is as good as a circle, dl. So this entire integration of dl means it is entirely the circle, and it is the circumference of a circle. So it is written as 2 pi r here. So now here what will happen is, see here children, this r into r will become r square, and this pi will get cancelled. So it will become mu 0 upon 2. So this is mu 0 upon 2. So this is the very important equation. This is a very important equation for the magnetic field along the axis of a circular loop. So remember children, this equation is a very important equation. Mu 0 upon 2 IR square Z square plus R square 3 upon 2. So you may note down children or take a screenshot of this. Now next, 10.14, this is the magnetic lines for a current loop. So see here, this is the current loop here, and see the magnetic lines. So see here, the magnetic field at a point P on the axis is given by. So we know along the axis what is the magnetic line, the Bz is equal to mu 0 upon 2. So that equation we have taken from that axial ones. So this is the equation. As a special case, the field at the center of the loop is obtained from the above equation by letting z equal to 0. But for the central one, okay, for the central one, z is equal to 0. Okay, then for the at the center of the loop, so it becomes b0, right? So b0 equal to mu 0 upon 2, because z becomes 0. So when z becomes 0, uh, this is 0 term, then this is r square. So 2 will get cancelled, become r cube, and r square upon r cube, so it becomes 1 upon r. So this b0 equal to mu 0 upon 2 I upon r. So this equation is nothing but the magnetic field at the center of the loop. This equation we have derived, but using the axis equation also, if you put z equal to 0, we are getting this equation here. Now suppose if for a coil of n turns, then what we do is we just multiply it by n. So B is equal to mu 0 upon 2 Ni upon R. So equation number 3. Now the direction of this is given by the lines is given by right hand thumb rule. Now see, what you have to do is curl the palm of your right hand along the circular wire with the fingers in the direction of the current. Okay, then the stretched right hand thumb then gives the direction of the magnetic field. So see here, what you have to do is curl the palm of your right hand along the circular wire with the fingers in the direction of the current. The stretched right hand thumb then gives the direction of the magnetic field. So you can see that this diagram is there. So you have to hold your palm, right hand with your palm in such a way that the thumb, it gives the direction of magnetic field. So this is the magnetic lines of forces. Actually it is shown, it is represented here. This is the loop, this is the loop, and this is shown, this shows the magnetic lines of forces. Now circular loop carrying a current as a magnetic dipole. Now we'll see here the behavior of the magnetic field due to the circular current loop at large distance is very similar to that due to the electric field of an electric dipole. So here we can see that it is at the large distance. Z is very much greater than R. that is at very far distance. That Z is there, but it is at very large distance. So it is so large that R is very small compared to Z, so it is neglected, you can say. So for BZ, so we are considering again BZ here. For BZ at large distance, that is Z, distance Z from the loop along its axis. So Z is very much greater than R. Therefore, BZ equal to mu 0 I R square upon 2 Z cube. So at the denominator, R is becoming 0. So you can have this equation. Now what you have to do is, in this equation, this R square is there. So the current of the loop is now loop is circular. So the area of the circle is pi R square. So now what you'll do is A is equal to pi R square. So here, instead of R square, you will write pi here. So when you multiply and divide by pi here, what you do is you just multiply and divide as if you are not making any change in this equation. So, but you're multiplying and dividing it by pi. So what will happen is A is equal to pi R square. So when you multiply and divide, so this part becomes A, and below there is pi. We have taken this pi. But this is at Z very much greater than R. The magnetic moment M of a circular loop is defined as M is equal to IA. And you know that IA is nothing but, actually we took last time, this is taken as M. That is the magnetic moment. M is equal to IA. Then BZ is equal to, so when we write for IA as small m, then this equation becomes mu 0 upon 2 pi m, m upon Z cube. So BZ equal to, now what you have to do is you have to bring this constant in the standard form. Always remember, that is mu 0 upon 4 pi. So when you take here 2, so you multiply also by 2 here. If you take down here 2 multiplied by 2, so it becomes 4 pi. So you multiply here also by 2. So mu 0 upon 4 pi is equal to 2m bar upon 4 pi Z cube. So using electrostatic analog, so like just like electric field, same thing. Here E vector, that is the magnetic electric field. E vector is the electric field, which is equal to 2p vector upon 4 pi. It's not E, it is epsilon, sorry, epsilon 0 Z cube. Now see here, 1 upon 4 pi epsilon 0 is the constant for the electric field. We have seen that Coulomb's law and all that, you know that it is 1 upon 4 pi epsilon 0. And that is also equal. Suppose here it is 2m vector divided by Z cube, whereas here it is 2p vector divided by Z cube. So there is similarity, or you can say there is analogy between this magnetic field vector and E vector along the axis. This is along the axis. Here only axis, what we are doing is we are taking it far away. In that case, R becomes 0 for the denominator. So this is the equation. You should know this. You should know the analogy between electric field and magnetic field. So you may note down this, children. It's very important because when you solve problems, you all should know what is the formula, where it is applied. You have to understand it and then solve the problems also. Then next part of this lecture is Ampere's law. It's a very important law in magnetic field. So this it is like, it goes on like this. See, you consider a straight conductor, and you know, when the straight conductor is carrying current, there are number of magnetic lines produced. You know that because of the current, electric current, magnetic field is created. So there are a number of lines, but for our simplicity, we have to find out magnetic field at some point. So you take a circle along that direction. So you're considering only one circle here. Okay. Then what is the statement? The line integration of B vector dot dl vector in a closed path is permeability times current flowing through the loop. So it's very important that the statement goes on like this: the line integration of B dot dl in a closed path is permeability times current flowing through the loop. So that it is equal to, so that is equal to B dot, closed loop is there, so we are taking as like this, we are taking this integration with the closed loop. B dot dl vector equal to mu 0 times I. So it is permeability. Mu 0 is a constant term, permeability times of current. So it's very important, this Ampere's law. Sometimes it is asked for 1 mark, state the Ampere's law. Now the application of this Ampere's law, we are going to see it for the straight conductor, then we are going to see it for the solenoid. And this solenoid, I told you, we have to, when the wire is wound in such a way that along a hollow cylinder, so that, and it is connected to a, what to say, battery, or you can say the electric field is applied to it, and then it behaves like a bar magnet. Remember, a solenoid, it behaves like a bar magnet. Now see here, application of Ampere's law. Now see, consider the same figure here. There's a straight line, that is a straight conductor. The current it is carrying is I. Consider a long straight wire carrying a current I. See here. B and DL are tangential. So we know that they are tangential to the Amperean loop, which is a circle. Which is a circle here. So you can see the DL, if you take, and this is both in the same direction, you know, if you take B and DL, they are in the same direction of DL, B. So thus B vector dot DL vector is equal to B dot DL. Actually it is B DL cos theta. This is a dot product cos theta. So cos theta is 0 because they both are in the same direction. So theta is equal to 0. So it is B dot DL. So we have written in the scalar form B dot DL, which is equal to B dot R d theta. So we know that DL is nothing but equal to R d theta. We know this. The field B vector at a distance R. The field B vector at a distance R from the wire is given by B is equal to mu 0 I upon 2 pi R. B is equal to mu 0 I upon 2 pi R. Okay, this equation we know. Now we are going to apply this equation in this the Ampere's law. So what we'll do is now see here, integration over the closed circuit or the closed loop, B dot DL vector equal to 0 to 2 pi. 0 to 2 pi mu 0 I. So now for B we are writing, substituting what? For B we are substituting mu 0 I upon 2 pi R, and for DL it is B dot DL, and for DL R d theta. So if you just go on simplifying, you'll see here R will get cancelled, and this is from 0 to d theta. Now d theta, you take it as theta, which is integration of d theta is coming theta, that is 2 pi for that. So if you write here 2 steps, it will become 2 pi. So 2 pi will get cancelled here. Integration of d theta, the steps you can write on your own, and then it becomes equal to mu 0 I. So this is the equation for the straight conductor. Now, if you want to write it, you may write it down. So write it down, children. The previous slide, first write it down. Sometimes it is asked for 2 marks. So you have to write the statement and prove this. This is for the straight conductor. Now the second application is magnetic field of a solenoid and toroid. Before that, solenoid. Now here I told you, if you solenoid is nothing but a wire which is wound on a hollow cylinder and is connected to the electric field. The electric field is there, or it is connected to a battery, you can say. So in that case, that solenoid, it acts like a bar magnet, and because the lines which are formed, because of that, it is like the magnetic field for the bar magnet. If you take a bar magnet, we know bar magnet. So you see here now, and you are going to take the cross section of it, of the solenoid. So it looks like this. Suppose this is a wire, so that wire is seen like this. The cross section is taken and you see the diagram of that current carrying solenoid. So see here now, solenoid. Consider an ideal solenoid as shown in the figure. So this is the solenoid. These are the magnetic lines of forces. Then for the application of the Ampere's law, an Amperean loop is drawn, which is shown in the figure. So we'll see it next on the next slide. It is like, it is taken as a rectangle. See from here, like this rectangle is taken. So that is the Amperian loop, we can say. And then this is the, this is the Ampere's law. That is integration of closed loop over B dot dl equal to mu 0 I. This is the first equation. Now, see here, I told you. So it is taken like this. Suppose this is the cross, this one. So Ampere's law is applied here for an ideal solenoid. So you can see that this is the loop, Amperian loop, A, B, C, D, A. So this becomes the loop. So over the rectangular loop A, B, C, D, the above integration takes the form like this. So now what you're going to do is, now for each line from A to B, B to C, C to D, so like this you'll take the integrations. You'll divide that integration, okay? So A to B, B dot dl plus from this B to C, see here, B to C, B to C, B dot dl plus C to D, B dot dl plus D to A, D to A back again, B dot dl, which is equal to mu 0 I upon mu 0 I. In the above equation, I is the net current encircled by the loop. So remember, I is the net current. Now see here, for simplicity, here B dot dl is exactly in the center and it is along the direction of B. See here, it is along the direction of B, this field. So B dot dl, integration of B dot dl is nothing but BL. Then we have 0 for this B to C. Why B to C is 0? See here, B to C is 0 because this conductor is perpendicular to B. That is, DL is perpendicular to B. So when it is perpendicular to B, cos 90 becomes 0. Then C to D is 0. Why? Why this is 0? C to D? Because this is far away from the conductor. This is far away. So here the magnetic field is weak. So it is as good as 0. So this is 0. And why A to D to A is 0 again? Because it is perpendicular to B. This DL, this element if we consider is perpendicular to B, so it is 0. So here, see here, you can see that the second and the fourth integrals are 0 because B and DL are perpendicular to each other. And third, that is this third one, is why it is 0. It is because outside the solenoid B is equal to 0 because here magnetic field is weak. So B is equal to 0. If the number of turns is N per unit length of the solenoid and the current flowing through the wire is I, then the net current coming out of the plane of the paper is I equal to, see, N is the number of turns, L is the length, see, L is the length of the conductor, and I is the current. So it becomes, if for this I you're going to substitute this, for this I you're going to substitute mu 0 I. So take the third equation. So this becomes fourth equation. So BL equal to mu 0, and for N I you're going to write NLI. So B is equal to mu 0 NI. Getting it? So this is a very important equation because once you know these equations, you can solve problems which are given in the textbook. Then please you may note down or take the screenshot because this question is asked. This is the application of Ampere's law for the solenoid. I have told you solenoid, it behaves like a bar magnet, or you can say a dipole. So take the screenshot. The last topic which I'm going to take from this chapter is toroid. Now toroids here, this you can see the shape like this. It is also cross section of that toroid. This is the Amperian loop, and the center one which we are taking is the one of this is the Amperian loop where you're going to find out the electric field, magnetic field. Sorry. So Amperian loop along the central axis of a toroid. So this is the central axis. So if you just take the solenoid and bend it in such a way that it becomes in this shape, it is as good as the tire of a vehicle, a rubber tube tire, or you can say rubber tube of a vehicle. Okay, and the magnetic field along the axis of the tube in terms of the current. Okay, we'll see that. And the this magnetic field is also how, you know, it is the concentric circles are there here. You can see there are concentric circles, and the direction of the field is given by the direction of the current in the coil around the toroid. Okay, so direction of field is given along the direction of the current. So you may see down, you may note down. So cross section is taken. So this is actually the wires are seen in this way, because there are number of turns. Though here there are little shown, but the number of turns are on the total toroid, on this full toroid. Now again, Ampere's law is what? So first always start with the Ampere's law. Integration of B dot dl is equal to mu 0 I. Now where I is the net current encircled by the loop. So remember that. Now this I is nothing but IN. Okay, so the current and the number of loops, isn't it? So this is the total current. Here N, here N is the total number of turns in the toroid, as the integration is over the full length of the loop. Remember, and that is nothing but full length of the loop. You know, if you take the full loop, it becomes as good as circumference of a circle. It is nothing but a circumference of a circle, that is 2 pi r. So therefore B is equal to, so that equation, see this equation modify. So B is equal to mu 0 In upon 2 pi r. So this is the equation for toroid, whereas for solenoid we have seen mu 0 In, and that is small n. Here it is capital N taken. So remember the differences and try to understand and read it. Read the theory again and again and go through the problems. If you have any doubt or difficulties, you may ask us anytime, or you can also you go on studying, and whatever are the questions given on the last page, go through that. We'll give you assignments later on. I think so next lecture I'll take some problems, some solved, there are no problems, but there are some solved problems. So go through those solved problems, go through the theory. And one more important thing which I want to tell you is that in your syllabus this year you don't have a 10.3, that is the cyclotron motion, and 10.4, that is helical motion. So don't solve the problems also for it, because you don't have it in your syllabus. If you want, you can go through. If you want to read, if you want to give some exams, you read it. Definitely we'll try to solve your problems if you have any problem. So next lecture we'll start with the problems. I hope you have understood this.